Okay, we will start. So our next speaker is Mark Horowitz from Stanford. Mark asked me to be short, so I will just say that a couple of years ago, Mark gave a talk at Technion, and I introduced him as the smartest person outside of the Technion. So this time I would say that he's the smartest person outside of Berkeley.
Thanks very much. I'm going to talk a little bit about hardware constraints, but I have this thing about not wasting people's time. I hate when people waste my time, and so I don't want to waste yours. So the first thing I want to do is, what would you like me to cover? Like, what aspects of hardware are you actually interested in? I mean, I play somebody who has built hardware. I've built a little hardware at Stanford. I'm not an industry person who's built a ton of hardware, but I've been in this field for about 40 years. And so I know a bunch about how hardware has been built in the past. So I'm happy to answer any questions. If I get dead silence, I have 70 slides I can go through. But I really would like to tune it to what you're most interested in. Yeah?
So are there new trends in hardware that algorithms could help if they adjusted to it? And
okay.
Are there new trends in hardware that are already there and must be answered by?
Yeah. Okay. Well, there are actually, and the good news and bad news for you is it's really going to be a lot on the algorithms design because hardware, the progress in hardware has been slowing down. I'll talk a little bit about what that is. And it turns out locality, I think, is everything. And dealing with basically data motion is probably the most important thing. And that's an algorithm thing, not a hardware thing. Okay, great. Yeah.
But I guess as we were talking before, I mean, it's essentially the same question, but just particularly about memory and some of the things that were brought up in the last talk, and how do you actually have a model of what costs are in accessing memory in various ways?
Particularly like the processing in memory part, I think, is interesting to learn.
Inside or right outside?
We'll talk about this because it turns out I think we both agree it's basically about locality and where you are. Okay, great. Other things, yeah?
Anything that you think that is relevant to matrix multiplication?
About what?
Matrix multiplication. Any hardware trends and challenges that are relevant to matrix multiplication?
Matrix multiplication, yeah. Okay. Topic of everybody's interest these days. Yeah.
Given that you do have 40 years of experience, amongst these interesting things that are popping up, any predictions on which ones are likely to catch on in the market? Like which one we should be focusing on, so to speak?
And who to invest in also.
Yes, that's
really. Well, I was going to say I'm not a wealthy man, but I actually did a startup, so my investment advice is not something I would pay for. Yeah.
Security, like when you can influence changing of computational bits or reading them, I don't know.
Okay.
Especially with all the trusted execution environment and hardware.
Yeah. Okay. Great. Yeah.
Kind of aligned with matrix multiplication, but are we going everything towards accelerators for like networking, security, specialization?
Yeah. Okay. I think we have some things. Fortunately, some of the slides I have will answer some of those questions, and some of them won't. So I'll pop in and out. So in terms of what technologies will emerge, let me start there because that's how my slides start. The talk about emerging technology is not new. In fact, about 20 some odd years ago, I gave a talk called Life After Silicon, an Oxymoron. I just copied a couple of the slides here because I'm now an old curmudgeon but as people told me, I was a curmudgeon even when I was very young. I think that, we talk about the end of silicon or the end of scaling, and at that time, 20 years ago, it was about the 100 nanometer barrier, not the 3 nanometer stuff that we're talking about today. But there was always talk about new devices and what kinds of things were going to emerge. Now, as I have no proven record at predicting the future, although this talk 20 years ago was pretty on spot. So I am a huge supporter of silicon and conventional technology. And so far I've been right, though the world's a little different now. So my executive summary 20 some odd years ago was people have been talking about the end of silicon for a long time. Most of the emerging technologies that people talk about were emerging 20 years ago. Like phase change memory, when I started the business in 1978, I worked on Algorithmic memory, which is a phase change memory, and it was going to emerge then. 40 years later, it's still going to emerge. So if you're asking me, I'm not betting on RRAM or on Algorithmics, right? On phase change memory. Scaling will eventually end, and I'll talk now about the fact that it has. But basically, the problem with emerging has to do with getting enough money to maintain the development to actually make a product. And that turns out to be very hard. So insertion strategy is the most important thing, and we'll talk a little bit about it. So when people talk about a new technology, the question is, how are they going to make the money that they need to make to improve it, right? And if you're competing against, and one of the reasons that emerging memory is extremely hard is because DRAM and flash have been designed and engineered, and I'll show you some pictures, and they're just amazingly complicated beasts. And if you're going to try to compete with them, they're the people who are making money right now. And it's very hard if you're not making money to compete with somebody who is making money. And that's the reason that NVIDIA controls the world, because NVIDIA is making money and everybody else is not. Okay, and it's not that they're better in any intrinsic way, it's just that they were there. And HBM, which is this magic memory thing, was created, I think, in 2013, 14. It was a really bad idea for about a decade because nobody bought any of them until NVIDIA needed it for their GPUs, machine learning things, and then it became the most important thing in the world. This was my old outline. My new outline is I'm going to talk a little bit about, I think, the most important thing from an algorithm person about where technology is going or where it's not going. And then we can talk a little bit about how to evaluate technology or what to think about. I'm going to answer the question, is everything going to specialized hardware? And the answer is yes. So that is happening. We're having specialized networking hardware. We're having specialized machine learning hardware. We're having specialized, for any application that's significantly large, we're building specialization for that, partially to deal with the fact that normal scaling is not doing so well. And then I'll talk a little bit about memory. And at that point, I'll probably break out of this thing, and I'll talk a little bit about what I think are reasonable memory models and what we can and can't do, and what people don't tell you when they talk about in computing, computation in memory or near memory. Okay, so I think, yeah.
Here's a question for prognostication. Do you think there will be a limit to specialization?
Yes.
Great.
There's a huge limit to specialization. And if you look historically, what happens is people build specialized engines, and then they realize, oh, these specialized engines are all kind of similar, and they build a more general engine, and that's programmable and does lots of things, and then they realize, oh, the efficiency of that is not as good as they could, and then they respecialize, and then they regeneralize. So GPUs, which basically rule the world today, were not initially programmable. They had lots of specialized stuff, and then they realized to do some of the graphics rendering, to do the complex renderers they needed to do, they needed a little bit more programmability, build some programmability in it. This is a different story, but NVIDIA was very worried about basically losing out because Intel was including GPUs in the base processor, and that was eating out the bottom of the market. They thought that they needed another market to go to. They decided they're going to try to do scientific computing, so they made their GPUs even more programmable. That was a bust. Their graphics performance wasn't as great because they spent some time doing this programmability. But when machine learning came around, it was the only programmable platform that had very high arithmetic computation, and they took over the world. And now they're worth more than anybody else. So the thing about predicting the future that I will tell you is that in almost all the cases where someone looks brilliant, it's because they made a decision that was a bad decision at the time they made it, that turned out later to be good. HBMs, bad decision in 2013. It was actually done as a competition to Rambus, which was the company I was involved with that did high bandwidth memory. And it was a way of proving to people you don't really need that stuff. It languished for almost a decade. Samsung, it was a JEDEC standard, made the parts. They stopped making the parts because nobody bought them until I don't remember, it's 2022 or whenever, machine learning started taking off in terms of the GPU, and it became a necessary thing. And now Hynix is bigger than Samsung, right? NVIDIA invested in scientific computing, which was never a big market, but it gave them the thing to be in machine learning because they had the programmable platform. So the answer is the best way to be ahead of the game is to do something that may be right in theory, but doesn't have a market yet, and then the market, and then you're the player there who has a part that can be used, right? And NVIDIA could do this because they had the graphics base. That was what they were making money on, and they could afford to do this, and they tried to move in a new place. Does that make sense? Yes. Okay, so technology scaling. The driver of computing, and we have been in an era where computation has basically become cheaper every year for the history of humankind. Because initially we had mechanical computers, then we had tubes, and then we had transistors, then we had integrated circuits. And it was, Gordon Moore back a long time ago built this plot that Dave Mooring showed before about scaling. Now, the whole critical thing is to realize that Moore's law is really about the manufacturing cost per component. And yes, you get more components per chip, but the reason you got more components per chip is because the optimal place that was most economically viable as technology improved was bigger chips, right? So it was about how to maintain minimum cost. And Gordon Moore, in a talk he gave 20 years ago, showed the cost per transistor from the late 60s to 2002 being this exponential decrease in cost per transistor. And that has really fueled the whole information technology business, right? When transistor cost scaled, making the same product in the new technology was always cheaper. So that meant that if I built a new technology, I knew I would have volume in it because people would move all their products to the new technology. So it was worth investment. That also meant that all high volume or growing volume parts were in the latest technology. And all fab development was always in the latest technology because that was what people would use because it's the way you made the most money. Okay, now I don't know if you've been paying attention, but if you have, you notice that the state-of-the-art products today are not all made in the latest technology. If you look at the AMD processors, the processor cores are made in the latest technology, but some of the I/O stuff in the processor core are not. So that should give you an indication that something's wonky going on. And what's really happening is, Dave didn't want to say this. I'm a hardcore engineer. I've been in the IC business for a long time. I piss off some of my fabrication friends. But Moore's law has ended, or Moore's law cost scaling has ended. Like, we're still scaling technology, but the cost is not scaling. And to me, that means it's broken. And this was pointed out in around 2000. This was the CEO of Qualcomm gave this talk about what it cost Qualcomm per transistor. And this was sort of the exponential scaling. It's not on a semi-log plot, which is the first hint that something's wrong. Right. And basically, it means that the cost per transistor has not really been scaling sub 45 or someplace around there. Okay. So that's the first thing. That data ended. You can look on the web. And the other thing that happens is that you go from 7 nanometer to 3 nanometer. So if these were really something that they should be, you should get 7 squared is 49, 3 squared is about 9. So you should get about 5x increase in density if those were real technology numbers. But if you notice from here to here, you get about a factor of 2. So the technology numbers are marketing. They're not really density or anything anymore. Okay, and it turns out when you go from here to here, you double the price of the wafer. You only double the density of the wafer. The cost per transistor is basically constant. And if you don't believe any of those, there's this great guy. This is like the most amazing website. He has been tracking the spot price of storage, both disks and memory, for 60, more, from the mid-55s to today, so 70 years. And you notice this semi-analog plot, so you notice that the DRAM prices have been coming down, and then you notice this oscillation over here. There's a small decrease, but it's basically flat. Disks are flat. SSDs are basically still falling, but I can show you later that their cost per bit is actually also not dropping as rapidly as it used to. So we're in an era where the cost per storage bit of memory or disk and the cost per transistor to do computation is no longer scaling. Okay, previously, like when we had the good old days, we could do, as Dave said, you got more functions, you got, they became cheaper, the energy decreased. Well, actually, we never decreased the energy quite as much. We got more performance out, but things were good. And then Dennard scaling stopped about 20 years ago, and so we still got more numbers, more gates per function, per dollar. The gates were a little faster. The energy scaled, but we were scaling things up, so the energy was going up, so power became a huge problem. But today, technology numbers are marketing labels, transistors get more expensive, and energy scales down a little. So what that means for you as algorithms, so this is the most important takeaway from technology, is that the base hardware you have is no longer getting better for the first time in human history. And there might be a new technology out there, but it takes a decade to actually mature technology to insert it into volume production. As of today, there isn't any technology, I think, out there that will take over. So I think it's reasonable to say for the next decade, and we'll see if anything new comes out, that we're in this technology. And for all the hype of quantum computing, we can talk about that too, it's not going to replace normal computing for a whole bunch of reasons. So I think we're in this situation, and that means that we have to do something else. So what are people doing? We need to increase efficiency. So how do you increase efficiency if the base technology is not improving? Well, basically, you increase the number of SKUs, the stock keeping units. You make different kind of products for different markets. And you optimize those products for different markets, because if you optimize it for a something, you can make it better. But that means that the market per SKU that you have is smaller, and you need to do more specialization. So that means you need to decrease the cost per creating an object, right? And you need to optimize the dollars per function, so you want to put the transistors in where you need them. And that's what really led to, or the main impetus for this advanced packaging things that Dave talked about, which is so-called chiplets. It's a way of selling you exactly the transistors you need for your part, and not having a general part that's more powerful than you need, because that would cost too much. Like before, it wasn't worth the effort. I'd just sell you a chip, and because it didn't cost that much. So I just want to point out that chiplets are what we're doing right now to continue to scale performance, but they're not the answer because chiplets don't fundamentally fix the problem. I mean, what I do is I manufacture this piece of silicon and I manufacture this piece of silicon and I put them together. I still have the cost of this guy and I still have the cost of that guy. And putting them together has some yield loss, so it makes it more expensive. And if I put this thing onto another piece of silicon, an interposer, like over here I have some interposer and I put all these chips down on the interposer, I have to pay for the interposer, I have to pay for the chips. That increases the cost per transistor. So it's not solving the problem. It gives me a little more flexibility to play, and it allows me much higher bandwidth connections between the things, so the communication, which is the fundamental problem. This locality, algorithms don't have as much locality as we'd like, so it makes that cost a little less. So we're doing that, but it doesn't fundamentally change the math. Okay, so there, you're putting things on an interposer. Initially, it's made of silicon. People are moving to glass because glass is cheaper than silicon, but it's still additional costs. Now, there's some questions about how this worked and why this worked. So if you're connecting a chip to a board, normally you would have something which is a solder bump, which is on the order of pitches of about 100 microns. If you're connecting things onto these interposers, you do micro bumps, and that's about 5 times smaller, so 25 times the density, right? And then there is new technology, which is chip-to-chip bonding, which is this hybrid copper-copper bonding, and you can get something that's around 2 microns. That works, but it's only face-to-face. So you can do that once. You can't do that more than once. So these are kind of the kind of connections that we can have, and that's the reason that we're doing the advanced packaging. Now, and all of this is happening, what you might say is a really bad time because, the LLM and the AI boom is having a huge demand for computation. Okay, so what are we doing to basically satisfy this? Is we're basically using advanced packaging, and we're taking this as an NVIDIA chip, and we're putting basically the memory very close to the chip to get higher bandwidth, right, to build the system, and then on the chip itself is using a lot of parallelism and a lot of memory locally to try to get higher bandwidth again. And then it just recurses down. So if you look at those memory, if you look over here, this is the GPU. These are the DRAMs around it, but these are not individual DRAMs. These are stacks of DRAMs. So what's actually happening here is this is your DRAM die. You literally drill holes all the way through the DRAM die, because I have to get a wire from this DRAM to this DRAM to this DRAM. So when you're doing stacking, you have to put holes, and there's a limitation in the size of those holes. So what that means is that when you look at your DRAM, this is an HBM. This is a public picture, so someone had a little oopsie when they did this. But this section in here are where all the balls, the through silicon vias are, and the high density. And so you're spending a lot of silicon just to do that. The DRAM arrays are on the top and bottom. Does this make sense? Okay. So if you were to look at sort of a cross-section through this, you can see the different kinds of connections that people can have. So these are the big balls that connect the interposer to the PC board. These are the small balls that connect the little chips, the DRAM stacks, to the interposer. And these are the through silicon vias that are basically connecting all the wires through the DRAMs themselves. Does that make sense? Does this make sense? Okay, sort of. So the important thing here is that we're all trying to deal with getting data. And the important thing to realize is that when we talk about in-memory computing, in which memory, right? Because the memory is each of these individual DRAMs. So if I'm going to do in-memory or local computing, it's going to be on, it's going to be on this DRAM die in this region right here, or in this DRAM die in this region over here. If we're talking about the memory, then it's got to be over, at the place that it comes out. So it's not as local. And if you look back in the previous picture, that's one stack. That's a different stack. That's a different stack. Does that make sense? So, so I think the point here is when we're dealing with things, we're trying to deal with how big a region do you have to go over to have the set of data that you want. And that really sets how much communication you need to do. OK, we're packing things tighter together because it gives us much higher bandwidth to get the data across. So this one has 500 or 5 terabytes per second from the GPU to the HBMs, and the current ones I think are 7 or 8 terabytes per second. And then to connect this to the other GPUs is another roughly terabyte of memory that goes to many of the other ones. And these machines all have the ability to access anybody's memory. Packing everything together allows me to get higher bandwidth, but doesn't solve the fundamental problems. Each of these chips over here, which actually, because this is actually 2 physical dies that are as big as they can be with 8 HBM stacks on it. This whole thing dissipates over 1 kilowatt. The board that has 2 of these on and a couple other things is 2.7 kilowatts. The rack that has, I think it's 32 of these things in it is 120 kilowatts. Right, that's, OK. And the next generation is the rack's going to be about 0.5 megawatt. And I don't think it said what the individual power was, but I think it's 2 kilowatts per module. OK, so it's amazing. And what that means is that when you build a system, you're actually not doing just electronics, you're actually doing plumbing, because there's no way to get that level of heat out through the air. The air doesn't have enough heat capacity. So these red and black cables, or the black cables, the red cables are power, I think. The black cables are the things that are distributing fluid in to basically get the heat away. And so if you look, each of these racks has these pipes from the main plant going in that basically have the hot and cold water that come out. Does that make sense? So you can imagine you have 100 kilowatts and water. And it's like, you worry about water leaks because that would be bad. The other thing that I think is just interesting is this was a talk from somebody from NVIDIA who came and showed us how the cooling system works. So one thing that's surprising, at least to me initially, is the cold water is at 45 degrees C. And the reason it's so hot is that eventually you have to expel that heat into something. And if it's colder, it's harder to get that heat out. So it comes in at 45 and it leaves at 55. So it doesn't raise in temperature that much. The entire drop through basically the cold plate to the attachment of the silicon is not that high. Almost all the temperature drop is literally in the piece of silicon itself. And that silicon is a very good conductor of heat. As Subhashi said, when you start putting the oxide layers in, it's not so good. And when you start doing metallization on both layers, as people are talking about, it makes the heat extraction actually harder. And so this is a problem for people who are stacking in other things because you're making the cold plate farther away. And that's just an issue in terms of total heat density. Does that make sense? OK, so one can think about, well, we started with mechanical computing, and then we went to tubes, and then we went to transistors, and then we went to bipolar transistors, and then we went to NMOS, and then we went to CMOS. If this whole technology is basically failing us, maybe there's some new great technology X that's going to save us, right? And I think right now, this technology is so wickedly engineered that the probability of a new fundamental technology coming in and saving us is not high. I'm not saying that it doesn't exist. I'm just saying, if I have this very fancy graph, which is like the amount of risk tolerance that people have given the amount of money you ask for. Like in the Bay Area, $1 million, or in AI this day, maybe $100 million, no problem for something. But when you start asking to replace silicon technology, you're talking about billions of dollars. People who want billions of, who need billions of dollars basically want their money back in some way. And so it's just, I don't see, in order to be different than silicon, it's going to be pretty high risk. And so I just don't see us getting there right now. So what that means is that we have to evaluate things that we can do in silicon and sort of different circuit architectures or things we add to silicon to make it better. So how do we evaluate a new technology? I mean, I think the only thing I really want to say here, and I'm going to skip most of these things, is this is the part that most people forget about. Like when you're talking about doing something, the most important criteria is design time, designer sanity, because you're building some very complicated thing, and you're going to have to spend time thinking about it. You want to spend your time at the place that has the biggest return. And therefore, you really want to simplify things as much as you can. Power dissipated is, I think, the next thing. Performance is the next thing. And then the area is probably the last thing, just in terms of when we're evaluating. So when people tell you ideas, you should be thinking about these things. Now, from a designer sanity perspective, you can have a lot of people spend time building some building block. Like DRAMs are amazingly complicated. But for us, that's OK, because someone did that, and I just reuse it. But if I'm going to build something complicated, you better reuse that thing and not tweak it, not have to tweak it for each instance. So mostly for designer sanity, you want to hide lots of issues in the thing. Why does everybody use digital gates? Well, because when you do analog design, sort of everything matters. You have to consider everything. For digital stuff, you don't have to worry about power supply noise. You don't have to worry about lots of things. You can just view it as a logical abstraction. But more than that, more than just digital, actually in modern designs, all gates have to be unidirectional. Right? You're only allowed in standard cells to drive the gates of transistors. You can't drive anything else. And the reason for that is you want to be able to assume that inputs affect outputs, but outputs don't affect inputs. Because if they affect inputs, then you have more things you have to worry about. Right? So we do these kinds of things. And then one of the magic of a CMOS gate, a CMOS gate has a really nice digital characteristic for a whole bunch of bunches in here. So it's a really nice gate. But the magic of CMOS is actually that it's one of the few structures, in fact, maybe the only structure I know of, where it doesn't dissipate any DC power. And when an input transition occurs, the output transition occurs without a clock or anything else having to happen. Okay. There is no analog circuit that can do that. If you have an analog circuit, you either need a clock or you need to dissipate static power. So, and that's the reason, like when I started designing CMOS circuits, I did all kinds of really interesting circuits that I'm not allowed to do anymore. Because the interesting circuits used pass transistors and did various things, but they didn't have all these isolation characteristics. And as the designs got more and more complicated, we got more and more constrained to make it simpler. The other magic of CMOS gates is that it's insensitive to device variations. It doesn't really matter whether the transistors are good transistors or bad transistors, as long as I basically switch on and off. It's easy to build large fan-out circuits. I can have a gate driving a lot of gates. And in fact, because the gates don't take any input current, Wire resistance only affects timing. There's a lot of things that I don't have to worry about. If I start having circuits that have current that flows through them, then I have a lot of other issues I need to worry about, and that's again, not bad, but something you need to, increases your design complexity. And then the real advantage of CMOS is that it doesn't dissipate any power. It's only every time you transition, you pay some power. And this is probably the other really important thing to think about. We always talk about communication is the problem. Well, the thing that consumes resources in CMOS logic is basically charging and discharging capacitance. The capacitance of a wire is proportional to its length, and therefore the amount of energy it takes is really related to the distance over which you have to communicate that piece of information. So fundamentally, if I move data less, I spend less energy, goodness happens. Make sense? And it's all because of this. Okay, so the capacitance is where I dissipate energy. And yes, the gate has some capacitance, but when I size gates, I size them to drive the load. And therefore, in every design that happens, more than 50% of the capacitance is in the wires, it's not in the gates. So to first order, from a theorist, you could just think it's wires. Make sense? Okay, now we get to the tyranny of CMOS. There's this dang thing called Boltzmann statistics that says, if I have an energy barrier and I want to control the flow of electrons, electron distributions in a Fermi-Dirac mumble distribution, and that means that as I change the barrier height, the current increases exponentially. The best it could do is increase exponentially with the barrier height. And what that means is if I want to have very low leakage current, that is when I'm turning the transistor off, I need to have the barrier high enough so that not very many currents go through. It means I need to switch a certain amount of voltage in order to turn it on. And that voltage is on the order of half a volt. We can argue if it's 200, 400 or 600 or whatever, but it's on that order, which means that there's a minimum voltage you can operate CMOS gates, which is on the order of probably 0.6 volts. And that means that if you think about the energy, it's the capacitance of the wire times like 0.6 volts squared. Okay. And if you want to be much more energy efficient, you would like to really drop the voltage. That's what we were doing for a long time with the NARD, but we had to stop because of this leakage problem. We needed a certain amount of voltage to keep the leakage low. Make sense? And in fact, we optimize the threshold voltages to minimize the total power, but that's a different thing. Okay, the other problem is that when you build the device, it doesn't always have exactly the same characteristics. There are statistical variations as well. When you're building something that has a large number of cells in it, you have to worry about 6 sigma variations because, if you have 100 million cells, that's still, you're going to get a number of those. So basically, CMOS gates are great because you don't have to worry about any of those. The variations don't matter. But when you get into memories or other things that are not true CMOS gates, it's a problem. And that's the reason in SRAMs, in modern SRAMs, you have all these extra circuits that boost things above the power supply and do various other things to deal with the variations. A typical SRAM cell will work fine normally, but with variations, you have to worry about that kind of stuff. So when people tell you that I built something in the memory and it works, okay, you can ask how big is the memory and what the margins are, because there's likely, as you try to build 100 million of them, the difficulty goes up. Okay, let me take it. So that's kind of where technology is going. I think basically the thing to think about from an algorithmic perspective is the base technology I don't think is getting much better. And the fundamental things that we care about is energy and performance. Both depend on sort of the length over the distance in which you have to communicate the information. And therefore, if you think back at all the things we do from an architectural perspective, it's always to bring things closer in to the things that we're computing. Make sense? Okay, so I said we're going to go to specialized hardware. And there are all these graphs that say, ASICs are much more energy efficient than everything else. Again, this slide is from 10 more years ago. The problem is that if you look at the energy breakdown in any processor, where this is the processor core, then it turns out half the energy in the processor is in the memory system. So you can ask the question about how does an accelerator basically get rid of this energy? Okay. And the sound truth is it's more about the algorithm than the hardware. So if you look at the space of all possible algorithms, there's a subspace of all possible algorithms that are GPU algorithms. And what I mean by GPU algorithms is they're basically SIMD parallelized. They have a huge number of tasks that are doing exactly the same things, or you're working on large vectors, because that's what GPUs do. And then if you think about building an ASIC or something like that, what you're really doing is you're moving in to something that has a huge amount of parallelism and very high locality, because that's the only thing that we can do very energy efficiently. Okay. So it's all about locality. And most people think when you build hardware, it's about specialized execution units and doing something. But really, specialized execution units are only useful if you have locality and parallelism. Because if I'm fetching data from all over, I need a memory system, and that's a memory system. Right? And in fact, as I do a better and better job at leveraging locality, I end up needing a memory system, because the better I do this, then whatever things doesn't fit in that little circle ends up needing to collect the data that I put into those little circles. Does that make sense? And so everybody starts building an accelerator and ends up building a memory system. And if you look at the NVIDIA or the TPUs, yes, they have the TPU, but really they have these amazing interconnections and everything else, because they're building this memory system to feed those units. Okay? And the truth is, because the application says locality, we end up tweaking the applications to get the locality that we need and to improve things. So from an algorithmic perspective, again, it's really about how do we think about these things and how do we maximize our ability to do local things. Now, another problem when you build accelerators is nobody actually wants an accelerator for a particular application, because they always want to tweak the application. You algorithm people, you always come up with better ideas and whatever. So you want an accelerator for a class of applications, which means you need to compile your application to the accelerator, which is the second big problem. So not only do you need to create the accelerator, but you need to create some software tool to use the accelerator, and creating the software support is usually harder than building the accelerator. Okay, so the big problem in building kind of accelerators is how do you translate algorithms onto that class of hardware? And I think another thing from an algorithm perspective, theory perspective, is there a better way of describing algorithms in such a way that will make it easier to map to different kinds of accelerators in the back end? And there's a project at Stanford that's looking at that. To make matters worse, chip design takes a few years. Applications change during this time. So Nafa Sara, who is head of Annapurna Labs, which builds a bunch of accelerators, gave a talk to people who are doing hardware startups. And he said, look, focus on optimizing the intended application is a mistake. Because if your hardware, when you ship it, actually does your intended application, that's like the best case scenario. That means you predict it right. Much more likely, the intended application is not going to exist when you ship it. And so what you really should be doing is spending time to figure out how to make it useful for the broadest class of applications, because who knows what it's actually going to be shipped in. So there's this tension between specialization and being able to cover a broader field. Okay, and here's the last part, which is really sort of the unfortunate part. Application designers are using current technology, and they want good performance. So what they do is they change their algorithms to map to the current machines, AKA NVIDIA, okay, to get good performance. When you create some great hardware, it probably doesn't have the same kind of trade-offs as the NVIDIA hardware has. And therefore, it won't be just compiling the applications, because the applications have embedded in it things that are for a different class of machines. And so if we could figure out a way of not embedding so much of the information about the hierarchy of the memory and how it's partitioned in the application when we write it, that would be another really good thing. Make sense? Okay. Let me just end a little bit by talking about memory, because there's all this talk about memory, and then I'll stop the slides and we'll just talk a little bit more. Now, the interesting thing is that this is Blackwell. So these are two, oh, here, it's easier to see here. This is one big as you can build chip connected to the same big as you could build chip with a interface between the two of them, because you couldn't build a piece of silicon as big as that you wanted. And then those two pieces of silicon are surrounded by these DRAMs, the HBMs. Now, if you look at that, and I asked you, which is there more silicon of, the DRAM or the GPU, you would say, looks like there's more silicon in the GPUs, right? Because they seem bigger. But remember, each of the DRAMs over here is a stack of somewhat like 12 die. Okay, so most of the silicon in the NVIDIA systems is memory. I'm not talking about the fact that this whole thing and this whole thing and this whole thing and this whole thing, and then in here, all these have got a ton of SRAM too. So I'm guessing if I looked deep into this thing, half of that's probably SRAM. But just calling that processor is still memory. Okay? So the problem with building specialized memory is that most of the silicon area in any system that we ship today is memory. And that means the cost of that memory is very important, because it's the most of the silicon. If you specialize the memory and you make that memory less dense, or you don't sell it in as much volume as the main memory, it's going to cost more money, and that means your system is going to be much more expensive. If it's a little more expensive, okay, but it's going to be much more expensive. So generally speaking, that means that you're not going to specialize all the memory. Maybe you'll have some specialized memory. But once you have some specialized memory, you have the problem of moving from the non-specialized memory into the specialized memory to do whatever special things you want to do, right? So if it's not all the memory, or a large fraction of the memory, I'm waving my hands literally. The memory is basically a computation unit. You have to move data into it and out of it. So if you really want to get the advantage of computing in memory, you have to do it in a way that doesn't make the memory much more expensive, because that way it will be in the memory wherever the data is, any place in your machine. Does that make sense? Okay. And the last problem, which I think is, again, a very interesting problem, and it's an interesting problem from a theory perspective, is when I have data and I'm putting it in a memory, I have to make a decision about how I organize that data in the memory, right? The way I do it in a conventional system is I splatter the data over all the memory I have. And why do I do that? Is if I randomly, it's a randomized algorithm, right? If I randomly place the data in the memory, on average, it's very hard to have a bad case. Like, no matter which data I want and whatever pattern I want, I'm going to get close to my maximum bandwidth, right? Because it's a randomized algorithm, right? Okay. However, it also means the expected case, the difference between the worst case and the expected case is small, right? So if you're trying to minimize the worst case, that's the thing to do. And oftentimes when you build a machine, you're trying to minimize the worst case, right? Okay. If I want to basically get the lowest energy performance, do all this processing and memory junk, we need to localize everything to have very high coherence. Okay. And what you've just done is you've maximized the distance between the worst case and the best case. Right? So to me, it is unclear how we should organize our data. Does that make sense? It's a question about, can, from an algorithmic perspective or whatever, you decide different classes of data have different characteristics, or there's some halfway in between that you get most of the benefit for the locality, but I think that's another interesting question about how you organize data. Okay. So you can ask the question, why is most of the silicon basically in memories? And memories are great because they have no communication. You have one wire this way and one wire that way. So for 2 n wires, you connect to n² objects. That's like the best. That's like a wire per 1/n. That's like, oh my God, great, great. And most of the cells are not doing anything most of the time. That's another great thing, because from an energy perspective. So it's a way of using lots of transistors with very little wires and very little power. So that's great. Now, we think about memories as being very simple. This is the schematic for SRAM, a DRAM, and a flash memory. But in reality, the technology that we use for building these things are amazingly complicated. So when people talk about like building something on a DRAM technology, the point is the DRAM technology is highly optimized. The transistors are like, yeah.
Going back to the previous slide.
Yeah.
Earlier you said that SRAMs don't really use just like standard CMOS transistors.
They use standard CMOS transistors. The problem is that when you're reading an SRAM, so a CMOS transistor has the characteristic, a CMOS gate has the characteristic that you drive the inputs, and the output basically drives capacitors. In an SRAM, the bit line capacitance is very large. So when you turn the word line on, this transistor turns on. And let's say this transistor was on, and this one was off. So that means this one's on. Okay? So when the word line is low, this is just 2 inverters connected together as a latch, which is perfect. You with me so far? Okay, once I turn the word line on, this transistor has to fight this transistor. Because this transistor's on, this transistor's on. And for this situation, the ratio of the currents between these 2 devices matters. Because I don't want it to disturb this value. I want to read this value. I don't want to write the value. And if transistors didn't have variation, this would be no problem. It would be very clear. The bottom transistor always wins. Okay?
So, but it's fundamentally caused by the fact that this thing is attached to a word line, which has got some big capacitance.
It's because it's attached to the bit line that has a very big capacitor on it.
So and if you just were connecting a bunch of CMOS transistors, then you wouldn't.
Yeah. So it turns out that you can avoid this problem if you make the bit lines short. So you only connect like 8 cells on a bit line, maybe 16. You don't have any problems either. It's much more robust. And so for very high speed SRAMs, you sometimes have smaller things. You have essentially a sense amp, which is just an inverter, on the local bit lines to drive the global bit lines. And again, you don't have any problems. But it's not as dense. Okay. Okay. So I'm going to stop this part. Let's see. I just want to, there's one other thing I just want to show you, which is, let me just show you a picture here because this is pretty impressive. So the way flash memories work is, what happened? Crap. Okay, let's try this. So the way flash memories work is you actually make many, many layers of silicon, and then you drill a hole through all those layers of silicon, and then every layer you pass through becomes essentially a cell. And so you get many cells. That's the reason the flash density has increased. But the problem is you can only make holes a certain aspect ratio. And so to add more layers, you actually build one of these, and then you build another one of those, and you stick them on top of each other. And when you do that, you're building 2 chips again, so the cost is not falling quite as fast as it would be otherwise. And then the other problem that you get is to connect, you have to connect to each of the layers. And so on the edges, you have these big amounts of area that just connects down. And that's not so bad because in a flash, the arrays are pretty big because it's not high speed. But when you start talking about increasing the performance, you end up, there's a trade-off. So flashes are not terribly local. And then for DRAMs, I just wanted to show that people think about a DRAM having these big banks and everything else. But the truth is, a DRAM consists of massive transistors that are maybe 1 million cells. They're now, it used to be about 256 by 256. Now they're probably 1,000 by 1,000. And they have sense amplifiers. These sense amplifiers are shared by the adjacent things. And so this is the local region in which you can do operations, right? If you have data over here and you need to combine it with data over here, there's like small amount of interface wires connecting these things together, right? And then these banks are basically, these maps are connected into what's called a subarray. The subarrays are stacked to form a bank, and then banks are basically put together on a DRAM chip to form the whole DRAM. So while people think about a DRAM being the memory, it's, again, locality play, right? Because if I'm trying to do something from here over there, I have to go across the whole DRAM. And the truth is, there aren't that many wires that go from here to there. Because DRAMs are very cost sensitive. They manage only the wires that they need. Okay, so even when you're doing things in memory, you have to think about the memory as being this hierarchical thing, and what is the region in which you're going to do the processing on. So people who are talking about PIMs are often talking about next to a bank to put some processing on it, but then you only have the bandwidth that goes out in and out of that bank. Make sense? Okay. So let me end here, and I'll go back to the questions we talked about just to make sure I've covered everything. Oh, crap. I didn't save it. Oh, shit. Oh, well, so much for that theory. OK, well, I'll stop here. I've got a couple minutes. Let me stop for questions, and I'll cover any of the things that you asked to cover that I forgot. Yes.
So to your point that the locality is highly important, are there any attempts to make locality accessible from high-level computer languages? Like there's L1, L2, L3, but even for that, you just optimize like cache line size.
Well, if you look at most algorithms that people do, most high-performance computing algorithms actually have been optimized for the memory hierarchy. Now, there are cache-oblivious algorithms that some theorists have done, which basically say, I'm going to organize my data structures and fetching in a way that it will nicely match the hierarchy, because I'm going to have many block sizes or something, so that when you have the caches, I'll do the good thing. Mostly, people have optimizations for reasonable size caches in the machine, in how they block the algorithm and do stuff like that. Oh, I know what I didn't do, matrix multiplication. So I think there have been lots of attempts. The interesting thing is that forcing people to think about the locality of memory would make things more local, but programmers hate it. So all attempts that have non-uniform, memory spaces, those programming models are not typically very popular. So I think an interesting thing is, how do you give people either the illusion or the ability to fetch things globally, because there are some things that you just want to be able to fetch, while still allowing or enabling people to take advantage of locality when it appears in the algorithm. And that's, I think, really been the focus. There was a question about matrix multiplication and any advances there. So what I will say is there's been tremendous advances in matrix multiplication. So fundamentally, I said the whole problem is getting the data to compute on. So previously, the way we did matrix multiplication is we had some vector engine, and we would fetch things into the vector engine, and we do the dot products, which is fairly efficient. The problem is that we would do all the fetches from the registers to do the dot products, right? And the fetches from the register was what was causing all the energy. And so we have moved from that to a specialized unit that does matrix multiplication by some systolic array that minimizes the communication, specializes the broadcast across the hardware unit for the matrix multiplication. So we have minimized the amount of fetching, and if you have a big enough 32 by 32 or 64 by 64, you amortize the cost of moving it into that special engine because you do 64 operations on it, and therefore the fetching into the engine becomes much less. Now, the other thing that's happened, as Dave Pedersen talked about, or we talked about before, is the precision that we're doing the computation in has decreased dramatically. So 8 is standard, and people are doing 6-bit, 4-bit kind of things. Now, if you think about multiplication, multiplication is quadratic. But the difference between quadratic and integer for small integers is not that big. And so once you're doing 8 by 8 or 4 by 4 multiplication, I don't think multiplication is very much of a big deal. It might be the adder that you do at the end is actually more complicated and takes a little bit more energy than the carry save as you have to do for that small number of partial product generation. So what I would say is that what we've done in that environment is really made multiplication very simple. In fact, for those number of bits, you could do a table lookup. For 4 inputs and 4 inputs, it's only 256 outputs. You could just right. Now that might be more energy than doing the computation, I don't know. But once you get to small integers, the computation is really not the issue. It's getting the data in and out. So because of that, one of the things that's happening these days is that people are doing essentially lookup tables to do the translation of the data into the computation you need to do. So what I transfer in is some encoded thing that maybe I give you only 16 values. You can write whatever 16 values you want. And usually there's an exponent that's on some block thing, so it's 16 values scaled a certain way. And it looks like some of the recent hardware is doing things like that. So from an algorithm perspective, another really interesting question is, what can I compute with all this low precision hardware? Because you could do amazing number of ops per second in 8-bit or something. And the question is, can besides machine learning, which everything is kind of not so good anyhow, can you do anything else useful with it? Because if you can figure out algorithmically or theoretically how to take advantage of the low precision hardware, that would be awesome. See, other things that are interesting from an algorithmic perspective in this area is that there's this notion about doing prediction and then checking. So basically, checking something is very easy compared to computing it, because checking never has any data dependencies. When you're checking something, you know everything, and you just need to run the algorithm. So it's easy to parallelize a checking algorithm. It's hard to compute something because in LLMs, you have this dependency and tokens. So what people are doing, and somebody here probably knows more about it than I do, is you're doing very simple languages models, much simpler language models to do prediction of what the tokens are going to be, and then you take the outputs of that, and then you basically run through a real model in parallel and check the tokens, and you're essentially doing speculation. So again, how do you take advantage of the simple computation to maybe do things that you can then later check? Or if you have an iterative solution, can I do an iteration or a couple iterations in a place that I can compute very rapidly and then refine it at the end? So I think those are all sort of interesting ideas that are being enabled by the hardware that's being generated today. Questions? Yeah.
I think you said that the only successful thing is everything is is SIMD that's successful?
Yeah.
You said- So,
Why is it?
or, I mean, so my programming of SIMD goes back, connection machine, but, the problem was you can't do branches, right? Because it serializes them. Has there been any progress on that problem in 30 years?
Well, I can, so NVIDIA has a threaded model. So it says that I'm putting all these threads together, but it is a SIMD engine at its core. And if you have divergence within the SIMD threads, its performance sucks, right? It's not very good. So what has happened is we really have moved to a data parallel model. Okay, and in machine learning, there isn't very many data-dependent branches, so this doesn't come in from the machine learning case. In the machine learning, the decisions you make have to do with which block operations you do, not within the block. I do not know, fundamentally the problem is that fetching an instruction takes a lot of energy. If I fetch the instruction and I operate on a single piece of data, the overhead of fetching the instruction and everything else is much greater than the operation of the data. So what I have to do is if I'm going to fetch an instruction, I have to do a bigger operation. Okay. Now, the easiest way if I want something programmable is I operate on a whole bunch of data because then I can have the program operate on a bunch of data and have a programmable machine. So everybody who's built a programmable machine typically operates in SIMD because that's the best way to reduce the overhead. And then we add these bigger computation units like matrix multiplication to make even more operations happen for a single instruction fetch. In other places where there's more decisions, like if you think about motion estimation or something like that, then what you do is you build special hardware that does the motion estimation step, and it handles the individual branch decisions locally. But even there, you can't get very much diversion in those threads because you have limited state machine control of that hardware. So I think the short answer is no, it's really not been fixed. It's still the same problem it was. It's just that it's the best hammer we have, so we still use it.
And it fits the graphics and machine learning applications okay.
Right, and in graphics, so what they do in graphics actually is if you have something that has splits of cases, you actually generate the outputs, don't handle the splits, and you do a sort. So you do a whole block, and you sort the threads that come out. Did you go this way or that way? You allocate them into a thread block, and then you run that thread block, right? So that requires some motion because you have to rip your thread blocks apart. But that's what happens if you want performance in CUDA, that's what you do.
It's particularly bad for graph algorithms, right?
Yeah, so graph algorithms, you can't really, well, in graph algorithms, what you typically do to take advantage of this, you organize the data so maybe the edge links or something are in a block, and you go and you fetch the edge links or something like that. But the truth is that NVIDIA has an amazing memory system. But if you have large diversity in the fetches, because I could have all these threads, they're all doing exactly the same thing. They all do a lookup, exactly the same lookup. It's the same instruction, but the lookup is like all over the world. That also fails miserably because it can't have that many outstanding references from every thread, right? Because the memory returns back blocks. And so if you're not using the whole block of data that the memory returns back, you're not getting all the bandwidth out of the memory. So it's locality. Like the thing is, DRAMs, these high bandwidth memories, right? We have enormously high bandwidth. If you want high bandwidth, you better be fetching blocks. Because if you're fetching random words, the DRAMs won't be able to fetch it. Other questions? Yeah, sorry.
Mark, there have been talks about that, when the cost per transistor is not scaling anymore, somehow maybe, we do something in other parts of the system, software cost and this cost and that cost, And as a result, overall, the system cost will scale, although the transistor cost may not scale. What's your take on that?
I think we will continue to innovate and make better hardware. So I believe systems will get more efficient, because if they don't, you don't have a product to sell. So it's kind of a necessity to make the system better. I do believe in those cases, most of the improvement is going to be on the software side and algorithm side. And even like, if you look at unit processors or processors and your laptop and everything else, most of the performance improvement has been not in the processor core, but it's been in the memory system and various things that assist in the prefetching or more accelerators for certain kinds of operations that make certain things better. So I'm not saying the hardware is not going to get better, because that would say that innovation stopped. I do think we're going to use various kinds of accelerators and things to continue to improve hardware. But I do think it will be very much dependent on the specific applications we're doing. And that's what I'm... Right. Was there another question over there? Yeah.
This is continuing on the algorithms side. So it seemed like two takeaways was, for an algorithmic designer, SIMD and locality together would give you
so
the
it's
Parallelism.
It's parallelism, but the problem with parallelism is if I have an independent thread of control for each parallel thread, fetching the instructions from that thread of control is very expensive, right? It's a fetch from some memory that's telling me something. So what I would like is I would like to amortize the thread of control over more data. And that's SIMD. What I need to do is I need to do block operations. So the project that we're doing at Stanford is called Portal. And the idea is that if I'm computationally bound, I have to be working on large amounts of data, because there's no sort of single thread thing that's that hard these days. Processes are pretty fast. Okay, so how do I conceptualize and talk about algorithms in terms of operations on the data, so that when I rip it to actually execution things, I'm thinking not about operations on scalars. I'm thinking about operations on tensors or graphs or something. How do I think about it in that way? And then does that give me the ability to build the data structures that include the acceleration kinds of structures we want for efficient implementations that could be tuned to the machine that it's going to run on rather than in my code directly? Right, so I want a higher level intermediate representation that talks about what the operations are. I can do fusion at higher levels. And then another thing that's, I think, particularly interesting that I'm interested in is what is the right abstract hardware model for all these frickin' machines? Because LLVM is what everybody uses to compile to processors today. LLVM is a very nice abstraction of a processor. It has infinite registers. It does, but it's an abstraction that everybody's machine is close to. If we look at all the machines that are coming out with this parallelism, what is the right abstraction level that we can have? And I'm arguing it is computational elements that have capabilities for operating on certain chunk sizes. So I don't care if it's SIMD or whatever, it's just a vector engine or it's a matrix engine, it does something. And then something about the storage and the bandwidth of those things that connect each other, right? So that's my view of a world, of the hardware world. It's kind of a data flow between these things. And it could be a uniform shared address space, right? But they're physically distributed memories. Make sense? Yeah, sure.
If you look on the supply and demand of computing, so for many years the supply was, according to Moore's law, double itself with the same cost. And now, even if there are improvements in the system, etc., still it's much slower than Moore's law. But on the demand side for computing, now the pace of the growing in demand is much higher than Moore's law, right? So does it mean that we will see computing become super expensive, that it means that it won't be able to even supply the demand?
So I think that my prediction from a sort of policy perspective is that I think computing will be, for the first time in human history, like electricity or power. That it is something everybody needs, but it is not something you have infinite amount of, and that you will get restricted, or restricted market, I don't know, but there will be a market cost, and the amount of computation you do is set by sort of market forces. And that's partially the reason I think all these projections about the amount of data centers and AI data centers are going to go, I think are a little unreasonable, because I think if you calculate the amount of money it will take to do that, you have to look at where that money is going to come from, and I don't quite see it, right? Unless we have a large displacement of people, and then where's the money going to come to support those people? Because if you don't support them, I think you have unstable government. So, I think it's interesting to think about costs. And there was another part of the talk that I didn't get to, but in the end, it all comes down to dollars. Okay, I'll be around. I'll stick around for a little bit more, but we're past the hour, so let me just thank everybody for your attention.
So at 2:30 in principle, there'll be coffee. And at 3 o'clock, we'll have our first talk, speaker that sort of started with an algorithms background and sort of did more systems research. So Bruce Maggs will give a talk, and the title is Health Monitoring with Wireless Sensors and Machine Learning. So I will see you sometime in 2:30 at 3.
Why do you say the coffee is in principle? Is that something I missed in the past, like yesterday it didn't happen or something?
It is scheduled on the schedule for 2:30. My favorite English word to teach the non-English readers is snafu. It's situations absolutely normal.
Okay. Maybe.